Welcome, everybody. This lecture is about inductive and deductive reasoning. So those are two types of reasoning that you see in mathematics quite a bit. And we are going to explore each of those with both examples from mathematics itself, as well as examples that you can see outside of mathematics. So hopefully you find that kind of interesting to see, this type of reasoning, which is mathematical by nature, employed within the subject as well as without. So let's head over, share my screen here, and we will take a look. All right. So we're going to talk about inductive and deductive reasoning. So here's a motivation. You've got 10 people in a room, and each person will shake everyone else's hand. How many handshakes will take place? We're going to come back to this, and you may be wondering, well, what does that have to do with reasoning? Well, we're going to develop our solution, and we're going to use one of the two forms of reasoning to arrive at some answer to this. Okay, so using specific examples to reach a generalized conclusion is called inductive reasoning. I think of inductive reasoning as the child in the back seat of the car saying, are we there yet? No. Are we there yet? No. Are we there yet? No. Are we there yet? Yes. Really? No, we're not there yet. You've been asking me time and time again, and every time you ask, what do I say? I say, no. So the next time you ask, what should you expect me to say? No. That's inductive. You have this experience or specific examples that's educating your expectations. And so that educated expectation becomes a generalized conclusion, okay? Now, that doesn't necessarily mean the conclusion is true, because after all, if the kid in the back seat said that long enough, eventually we would actually be there, right? But at least in the short term, you can expect that conclusion to be valid. No, we're not there yet, okay? You also think about it expectationally, right? Like if I were to tell you to continue this list, 1, 2, 3, 4, 5, you would probably next say 6, 7, 8, 9, and so on, because you've looked at the way I'm counting and really made an assumption. Oh, he's going up by 1 every time. 1, 2, 3, 4, 5, 6, okay? So that's inductive reasoning. And we can look at some examples as well. So let's do that here. Let's see. All right, so here's some non-mathematical examples. When you get in your car and you turn the key, you don't expect that, right? Now, is this a possibility? Is your car exploding a possibility? Well, yes. After all, there's flammable liquid called gasoline, and there's a spark. But do you expect it? Well, no. Rational people, non-mob members, expect to turn that key and everything to be fine, right? That's inductive reasoning, right? Every time you turn the keys in your ignition and expect your car to turn on, you are reasoning inductively. Your conclusion is that when I start my car, it will not explode. Here's another one. Oh, this nice couple is fixing up an old home. They're walking on that second story or attic even. Oh, when you're walking around the second story of a building, do you expect the floor to fall through? Most people do not. That's inductive reasoning. When I am upstairs, the floor won't break. That is an example of inductive reasoning. If you're sitting downstairs somewhere, there is no way to be 100% sure that when you go upstairs, you won't fall through the floor. Now, I'm not trying to make you paranoid or walk around the world thinking that disaster is imminent, but the reason that we all consider that to be so irrational is based on inductive reasoning, right? When I go upstairs, I'm not going to fall through. How many second stories have we been in our lives? Our experience tells us, don't worry about the floor falling through. Inductive reasoning. Well, there's mathematical examples as well. Predicting the next number in a sequence. So 1, 2, 3, 4. Well, inductive reasoning would say that the next number in the sequence turns out to be, and you're probably thinking it just as soon as you, sorry guys, you're probably thinking it just as soon as you read this list, but that next number would be 5, right? How about 2, -4, 6, -8? Well, there seems to be a pattern going on, right? We see evens, 2, 4, 6, 8, and we also see alternating signs from positive to negative. So you would probably expect that next number to be, well, first of all, negative, right? Because we're observing the pattern of positive, negative, positive, negative. And then 2, 4, 6, 8, 10. So we would expect that next number to be -10. Again, we're just using what we're observing to make that prediction. And does that mean that the next number absolutely is -10? No, but based on the information we have, that is the best guess we can come up with. It's the most reasonable expectation. How about this? 2, 4, 8, 32, 256. Well, what do we see here? Do we have any idea here what's going on? Well, let's see. Seems to me, and here you might need to do a little work, but it seems to me that 2 times 4 is 8, and 4 times 8 is 32. Oh, you see a little pattern here? 8 times 32 is 256, and so this next number will probably be whatever we get from 32 times 256. 32 times 256. That's 8,192. Okay. All right. So again, this is inductive reasoning. Here's a mathematical example. Let's say in some crazy world, maybe, I don't know, back in March, that 5 people were infected with a new virus. On March 9th, 10 people were infected. On March 14th, 20 people. By the 19th of March, 40 people. Now, epidemiologists, those in the medical field, health officials, public health officials, are going to look at this data and they're going to say, okay, let's see, March 4th. On March 4th, we had 5 people. And then on March 9th, there were 10 people. March 14th, there were 20 people. And then on March 19th, there were 40 people. And so what you might notice here, hopefully you notice, is that you've got these intervals of 5 days, right? The 4th to the 9th, the 9th to the 14th, the 14th to the 19th. And so you have this observation. And the observation is that the number of people infected, doubles every 5 days, right? It went from 5 to 10, 10 to 20, 20 to 40. And so you could use inductive reasoning. So inductive reasoning tells us 80 people will be infected by, well, 5 days later, which is March 24th. Okay. That's an example of inductive reasoning, okay, where you're making a generalized conclusion based on some observation, okay? Hey, how about a conjecture? All right, so that's essentially what we're doing. That generalized conclusion is a conjecture, taking those observations and generalizing them to some larger context, trying to even maybe make a rule, if you will, out of what you've observed. That is what we do when we make a conjecture. So let's go back to these 10 people that are all in a room. And let's see if we can arrive at a conjecture. So what I'm going to do is I'm going to simplify this and then slowly make it more complicated. So what do I mean by simplify the situation? Well, 10 seems like a lot of people to shake hands and count handshakes with. So you know what I'm going to do? I'm going to start with 2 people. So when there's 2 people, how many handshakes? Well, I'm going to represent those 2 people as dots, and I'm going to represent their handshake with a line segment, right? They're connecting. So there is 1 handshake. So notice that if you meet somebody and shake their hand, you don't usually say, okay, now it's your turn, shake my hand. No, you exchange 1 handshake. So 2 people, 1 handshake. What about 3 people? Well, let's put those 3 people together. 1, 2, 3. All right. Starting with the lower left, this person in the lower left is going to shake hands with the second person and the third person. Whoops. The second person on top here will have already shaken hands with person number 1, so they only have left to shake the hands with person number 2. And then by the time you get to the third person, they will have already shaken everyone's hands. So how many handshakes? Looks like 3 handshakes. All right, well, let's go to 4 people. Do we see a pattern yet? Maybe some of you do. Maybe you don't. But let's go on anyway. See, because if you do see a pattern, which I'm not sure you would at this point, if I hadn't done this already, I wouldn't necessarily see a pattern yet. But if you do, then you might ask yourself whether or not it works on the next example or the next case. So 4 people. Again, I'm going to start in the lower left and work my way around the square that I've drawn. So line segments. This person in the lower left is going to shake hands with the person above them, across, and next to. And then I'm going to work my way to the second person. They're going to shake hands with the person across from them. They've already shaken hands with the person below, so then they have to shake across. And then when I get to the third person, well, they've shaken hands with everyone except the fourth person. And so we count. 1, 2, 3, 4, 5, 6. 6 handshakes. Well,
maybe we can think about what we observe here. If you look at the corners, right? This person in the lower left shakes hands with 3 other people. This person in the upper left has already shaken hands with the person down in the lower left. So they only have 2 people to shake hands with because they've already shaken hands, right? And then when you get to the person in the upper right, well, they only have 1 handshake to make. In this lower right, well, they've already shaken hands with everybody. In the 3 people case, whoops, I'm sorry. In the 3 people case, lower left, they shake hands with 2 people. Top shakes hands with 1, and then 0. 2 plus 1 is 3. The 2 people case, well, 1, 0. So let's see here if we can generalize. Maybe we'll do one more before we try to get up to 10. So 5 people. I'm going to say 1, 2, 3, 4, and 5. I might move that one out a little bit. Okay. All right. So let's count them. 1, 2, 3, 4 handshakes. And then working my way clockwise. 1, 2, 3 handshakes. And then 1, 2 handshakes. And finally, 1 handshake. And when we arrive at the person on the lower right, well, they don't need to find anyone to shake hands with because they've already shaken hands with everybody. And so 4 plus 3 plus 2 plus 1. We have a total of 10 handshakes. Okay? All right. Well, now I think we see a pattern, okay? So for 10 people. Now, the more people I get, the more congested my line segments are going to become, and it's going to start to look rather dense. It's going to become harder and harder to count. But we do see a pattern now, right? 10 people. If we look at these other examples, we could think about the sum, right? We started with 2 people, 3 people, 4 people, 5 people, and we made this observation about how many handshakes take place at each node. Every one of these vertices I'm calling a node. And so that 10th person, or I should say the first person, has 9 people to shake hands with. The next person has already shaken 1 hand, so they have 8 people to shake hands with. And so on, right? Again, this is our conjecture. And so what do we get? Well, you could add all these up. You get 45. Now, one of the ideas we're going to explore in a lab that we do together is this question. What about in people. In other words, what happens if we have some number of people, we don't know how many? In other words, can we come up with a formula, right? Can we find a formula that tells us how many, that tells us how many handshakes will occur based on the number of people? Okay. So we're gonna explore that later, but I'll leave that for you to think about. All right, a counterexample. A counterexample is a single specific case that proves a statement false. A single specific case that proves a statement false. What do I mean by that? Well, let's look at some. If x squared equals 4, then x must be 2. Well, if x is equal to -2, then x squared also equals 4. So no. X doesn't have to be 2, and there's a specific case. All prime numbers are odd. 2 is even and prime. So no, that statement is false. All prime numbers are odd is a false statement. Why? Well, because I just found a number that is odd. I'm sorry. It's false because I just found a number that is even as well as prime. Okay. How about some non-mathematical examples? All professors are socialists. I know that's kind of a theme that you hear. Well, you promise not to tell anybody. I'll let you know that Professor Lewis is not a socialist. Okay? Counterexample, right? You're making a statement about all professors. So you just find one, you've proved the statement false. All Democrats support abortion, right? Again, this is non-mathematical, but we certainly walk around the world with these impressions of different stances that different people take, often based on political party. And one of them is that, oh, Democrats must support abortion. Well, is that true, that all Democrats support abortion? Well, that's actually not true. Okay, there have been several. So you could, I could give you a name. Teresa Bukovac, okay, Democrat, does not support abortion. They're out there. You can find them. All right. So you can see this example being played out, this notion of proving things false using a counterexample played out both in mathematics as well as just in standard conversation. All right, there is another type of reasoning that we're going to talk about. And if you want to maybe pause the video here, I would feel free, I would maybe invite you to do that, kind of rethink about the inductive reasoning. But we're going to now go on to deductive reasoning. So a conclusion reached through application of assumptions, procedures, or principles is known as deductive reasoning. We're not observing a pattern. Instead, there is a set of rules that we are following that lead us to a certain conclusion, okay? So here's a non-mathematical example. What in the world is that? Oh, that's Ponarag. Ponarag. Yes, this individual's name goes by an acronym. Person of non-assumed race and gender. Nonetheless, this person of non-assumed race and gender is on a camera going into a house. Inside that house is a jewelry box filled with, well, jewelry. This person's fingerprints are found on the jewelry box. Therefore, in true TV detective fashion, Ponarag stole the jewelry. That is deductive reasoning. We have a set of facts. We are combining those in logical succession to draw a conclusion. If they're seen on video, if there is jewelry found in that house, and if their fingerprints are found on the box that contained the missing jewelry, then we are stating and claiming that this individual stole the jewelry. You see this played out in legal trials all the time, okay? Deductive reasoning is really a fundamental piece to argumentation. Yeah. How about some mathematical examples? If 2x plus 1 equals 7, then x equals 3. This, most people will see 2x plus 1 equals 7, and they're going to go solve it. And so what's happening is when you go and solve something like this, you're saying, okay, well, 2x plus 1 equals 7. If 2x plus 1 equals 7, then I can subtract 1 from both sides and still get a true statement. So if 2x plus 1 is equal to 7, then 2x has to be equal to 6. And if 2x is equal to 6, then when I divide both sides by 2, x is equal to 3. We've applied a series of rules, right? If you think about your rules for solving equations, right? If you have an equation, subtract the same number from both sides, you maintain the equation. You can divide both sides by any non-zero number, you maintain the equality. And that leads you to x equals 3. So solving equations is an exercise in deductive reasoning. And here's another example. Sorry, that one kind of went too far. If A is less than B, then what can we say about the relationship between A plus 2 and B plus 2? Well, we can say that A plus 2 is less than B plus 2, right? If I have less money than you and we each get $2, I still have less money than you. Again, deductive reasoning. We are starting with this assumption. If that assumption is true, then what I'm circling is also true. Okay, so gave you quite a bit of information there. Hopefully, big picture, what I would love for you to walk away with is that this mathematical way of thinking can apply not just within mathematics, but outside the field of mathematics as well. This course is going to surprise you. You're going to have these moments where you don't feel like you're necessarily doing mathematics, but mathematics is a way of thinking. And I really want to impress upon you how to think mathematically. And thinking mathematically goes well beyond simple arithmetic. It extends to the way we think, period. Okay? So please try some homework problems, work through them, and be ready to have a good discussion about inductive and deductive reasoning. I will be back with you soon. Until then.